results in this course, and he was telling us, he told us several stories about the correspondence with Lazarus. Lazarus was a student in Brown, he had just left, I think maybe 2 years before, something like that. In any case, it was just in that period. And that time I saw him really excited. It felt like this was a big result. So that's the first memory that I have. Then, well, Fyodor has come many times to Italy. I just want to remember in 2006 when in Italy, every 2 years, we had a conference for young algebraic geometers, like PhD. They just finished the PhD. And usually we invite senior speakers to inspire these young people to enlarge their knowledge. And in 2006, we invited Fyodor, and it was really very nice. He interacted a lot with the students. It was very inspiring to them, and I think many of them are still benefiting from this. And last thing I want to say is that in my personal mathematical life, I counted at least 10 papers that come from understanding Zach's theorems and Zach's ideas. So, and as a matter of fact, the one thing that I really would like to outline is that if you understand well these things, then sometimes you get a big simplification, because he has a very clear view of what are the fundamentals of algebraic geometry. And if you understand the fundamentals, sometimes you can make proof of complicated results in a very simple way. Okay? This, I don't want to make a list, but for example, we can talk about classification of Fano triples. The series of papers that I wrote with Gilberto and Miranda, they come from an idea of Zach. Classification of Mukai varieties. Of course, they were classified before, but we did the classification again using this idea in very short papers. Very simple, very simple. In fact, simple in real algebra, basically. And then later on, with our collaboration, we studied the so-called Enriquez Fano threefolds, and I could make a longer list. I will not, because now it's not my talk, but it has been really a pleasure to understand at least some of your ideas and to use them at best. Yeah, so thanks a lot, and happy birthday. Thank you. Okay, so now I come to my talk, and first of all, I will make an introduction. So in this introduction, I want to point out one very simple thing, that there is a big difference. We all know, but I want to stress it out. There is a big difference between codimension 1 subvarieties and higher codimension subvarieties. Okay? And we know that there are several reasons, but as far as I understand today, the main reason is positivity. There is a very clear notion of positivity for divisors, and there is not a clear notion of positivity for higher dimensional cycles. And I think this makes a big difference. Of course, there are other reasons, but I think this really makes a big difference. And you know that there are important problems in higher codimension, like Hodge conjecture or Grothendieck standard conjectures and so on. There are several important problems. I don't have any idea why we are unable to prove them, but could be that the lack of positivity is one of the reasons. Okay, could be. I'm not sure. So let me start with some notation. So X would be a smooth projective variety of dimension n. This is over any algebraically closed field, any characteristic. And I'm going to fix an integer k between 1 and n minus 1. And I'm going to consider k cycles. So first of all, let's just say, I will speak about divisors and I will speak about cycles, and they will always be real divisors. So when I say divisor, I mean a real divisor. Divisor with real a divisor with real coefficients, and the same for cycles. Okay, so the notation will be zk of x is the set of, so this is the set of k cycles, real k cycles, And you all know what this is. This is just a linear combination of AI and ZI, where AI are real numbers, and ZI are subvarieties of dimension k. Subvarieties of vector dimension k. Okay? And two cycles are said to be numerically equivalent. So numerically equivalent. If, well, we all know this, but I want to establish some notation. So if they intersect in the same way with subvarieties of complementary dimension, right? So for every W containing X of dimension n minus k, and then one introduces the group of k cycles modulo numerical equivalence, which is called K of X. The group, sorry, the vector space. I said it's real. So this is a real vector space, and it's finite dimensional, and it will be equipped with the. So this is finite dimensional real vector space, and will be equipped with the Euclidean topology. Okay, so inside this we have several cones that I'm going to consider. First of all, we have the cone of effective cycles. So it's now it's alpha in K of X. So it's a class such that alpha is the class of E, where E is an effective cycle. Of course, an effective cycle is just a cycle that has non-negative coefficients. Okay, so it's good, no? And then we take the closure of this, and we call it self-effective cycles. So this is just the closure in the Euclidean topology. These are called self-effective cycles. Or I will just abbreviate self. Okay? And the interior of these two, which of course is equal, is called the big cycles. And this is the first notion of positivity. A cycle. I will talk about this a little bit later on. And finally, we have net cycles, which of course are cycles alpha in K of X, such that alpha times W is non-negative for every, or if you like, it's the dual of f n minus k, but in any case, for every W containing X of dimension n minus k. Okay, so these are the concepts we're considering. And now let's start pointing out what is different in the case of divisors and in the case of higher dimensional cycles. Okay, so we make a quick excursus in the case of divisors. So k is going to be n minus 1. Well, in the case of divisors, as I said before, we have ample cycles. Ample divisors. So it's the class D such that D is ample. And the important theorem is Kleinman's theorem here. I mean, there are several reasons, but this is one of the important. Kleinman's theorem says that the closure, well, in fact, it's enough to say this: ample cycle are just the interior of net ample divisors. So ample divisors are the interior of NEF divisors. Okay, so in particular the closure of this is the NEF cone and so on, but you can just write it like this. As a consequence, since of course any ample class is effective, well, it's not, yeah, if you like, it's a consequence of Kleinman's theorem. So, consequence. So if you take the NEF cone, it's contained in the set. Okay, because of course NEF divisors are limit of ample divisors. Ample divisors are effective. I mean, I'm talking about up to numerical equivalence. So you're allowed to take multiples and then divide. So they are effective, and then of course they're continued. Right? So the first difference between codimension 1 and higher codimension is that this phenomenon is not always true in higher codimension. Okay, so the first point. This fails for 2 less than or equal k less than or equal n minus. Okay, so this is a clear problem for several reasons. Okay, so there is these examples of the bar fine Lazarsfeld in Voisin. This is 2011, and there's also some more recent examples of Optem, 2015. So they prove that for every n, well, Optem is in dimension 4, I guess, right? Yeah, you can, right. So they prove that for every n, there exists an x of dimension n such that the inclusion is not true anymore. So for every n is 4, there exists a smooth n-dimensional variety such that the NEF k of x is not contained in set k of x for every k from 2 to n minus 2. Okay, so
could you write down one example?
Explicitly, this, as far as I remember, the examples are product n times an elliptic curve with complex multiplication. For example, the examples in the bar and Lazarsfeld Voisin, and they are constructed via differential forms. But explicitly, the formula is quite complicated. Yeah, no, maybe in his paper there is a more explicit example. But,
yeah, I think C2 of electric.
Yeah, so your example is a Fano variety of lines in a cubic, and then you take C2.
The first would be product of 4 elliptic curves with complex multiplication.
I'm sorry?
The first would be product of 4 elliptic curves with complex.
Exactly, yes. Okay, so these examples say that in some way we are supposed to look somewhere else. If you want to understand positivity of cycles, either we make different definitions or we are supposed to look somewhere else. So my approach was the following, so now I come to part 2, which is stable base loci. So now the introduction is finished. And I will talk a little bit about stable base loci. So, for divisors, so the idea still comes from divisors, but then one tries to generalize. So for divisors, there is a way to understand positivity in terms of base loci. Okay? And let me recall a little bit how this goes. So we have D, a divisor on X. So again, divisor means a divisor with real coefficients. Okay? Then we define the R-linear system of D, which is simply the set of effective divisors E such that E is R-linearly equivalent to D. And then we define the numerical base locus. Okay, so this is X if the R-linear system is empty. So if there is no effective divisor, if D is not effective numerically, there is no effective divisor, not numerically actually, linearly numerically. So if there is no effective divisor linearly equivalent to D, and otherwise you take the intersection of the support of all these forces. So it's like the linear system, but you take R real equivalence instead of linear equivalence. Okay, so. So this is the numerical base locus of D. This guy is not very good for several reasons. For example, it's not the numerical invariant. You may have divisors that are numerically invariant but have different numerical base locus. No, sorry. No, this is defined numerically, so this is numerically invariant. There is another base locus, but which is like, for example, if you take Q linearly equivalent. But no, this is, sorry, I was going to get into something else, which I don't want to. So now, after this, one cooks up two more base laws.
What is this? You use R equivalents, not numerical equivalents, right?
Oh, yeah, right. Sorry. If you put numerical equivalence here, there is numerical invariance, otherwise it's not, yeah.
But right. No scheme structure, right?
No, this is just a set, yeah. It's just a set. Even though over Q there is a possibility of putting a scheme structure using multiplier ideals. But over R, I don't know. Yeah, everything would be set theoretical here, huh? I mean, from this point of view. Okay, so one defines two more stable base laws. Right? This is the augmented stable base locus. So it's the intersection of the numerical base locus of D minus A, where A is an ample divisor. A ranges over all ample divisors, and then you intercept these guys. And then, so this is called augmented. Augmented stable base locus. And then you have the restricted or diminished, let's prefer, stable base locus, which is the union of the numerical base locus of D plus A, where A can transform on number divisors. Quickly, this is always a closed subset. This is not necessarily a closed subset. There are examples. This, in general, is a countable union of closed subvarieties, but not necessarily closed. They were introduced first by Nakamaye and then more recently studied by Hein, Lazarsfeld, Mustasa, Nakamaye, and Papa. There is a lot of results about this, which maybe some I will recall later. But let me just stress what is the relation with possibility. So you have that D is big if and only if D plus of D is properly contained in X. D is ample if and only if D plus of D is empty. D is self-effective if and only if D minus of D properly contained in X. And D is NF if and only if D minus of D is X. Okay? So the four positivity properties of divisors, they just are, if you want to detect them, you just study stable base laws and see what happens. Okay? So my plan when I started thinking about these things, my plan was simply, okay, why don't we start from this side? Now let's work with cycles. So we start from this side, we define stable base loci, and then we see what kind of positivity they lead to. They lead to some notions of positivity, and let's see whether these are good or not. Okay, and that's what I'm going to tell you. This is, by the way, this is very much work in progress. Okay, so I have some results, but there is still really a lot to do. Okay, so let me say how we do this for cycles. Okay, so now definition. Let alpha be a k-cycle. Then we make more or less the same definitions, right? So we define the numerical base locus of alpha, which is, sorry. First we define the numerical linear system. So we define. So this is in fact a little difference with respect to this side, but then things I will not show you, but things coincide anyways. So we define the numerical base locus of alpha, which is the set of k cycles C such that E is effective and is numerically well, and the class of E is alpha. Okay, so it's like numerical, say. Well, it's not a linear system, but in any case. And then we define the numerical base locus of alpha. So this is x if alpha is not effective, which you can write like this. And otherwise, it's the intersection of the support of all these guys. Okay. Then we define the augmented base locus of alpha. So this is the intersection of the numerical base locus of alpha minus an intersection of ample divisors, a complete intersection of ample divisors. So A1 times AN minus K. And here we vary A1 AN minus K ample. It's very similar to that. And finally, we define the B minus in the same way. We just put minus here. Maybe I can write it down.
So when you say intersection, the ample divisor need not be effective. You replace it by effective.
I'm sorry?
Ample divisor need not be effective. So
No.
you replace it. No
But here I'm taking the class in the numerical group. This is the class in modular numerical equivalence.
I is replaced by an effective divisor. You take the intersection of the other ones. It's effective, yeah.
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 Okay, then we define the B minus of alpha similarly. So now it's the union over ample divisors of the numerical base loci of alpha plus the class of this complete intersection. Okay, so this definition is very natural, and let's see what it does for us. Okay. Oh, by the way, first remark: if k equal n minus 1, they coincide with the previous definition for divisors. Okay, so this is not something new. I want to make two remarks. So one, with k equal n minus 1, they coincide with it. The class of D, D minus D. Even though the definition is different, but it's very easy to prove that they coincide, and nothing. The definition is different only because here we take numerical equivalence instead of R linear equivalence. But it's very easy to prove that they coincide. It's not a big deal. On the other hand, I think for cycles, once one goes to cycles, it really has to do with numerical equivalence, because for cycles there are notions like rational equivalence and so on. But I don't think they're very good for this type of purposes, as far as I understand it. Okay, the second remark that I want to make is that a cycle alpha, maybe to justify a little bit this, alpha in K of x is big, if and only if there exists some ample divisors and there exists an effective divisor such that alpha is the sum of these two. Okay? So this type of situation is justified also from this point of view. Okay, so let me start introducing the following cone. Maybe I should write it here because I will use it. So what's the possibility? Let me introduce a cone that will be for me the positive cone of cycles. Well, I'll try to write it here. So 3 positive cycles. Okay, so I define pk of x, which I call the cone of positive cycles. I don't dare to call it ample cycles because there are already other definitions of ample cycles, and well, in any case, maybe if anyone wants to understand, I will maybe tell something later on. But in any case, so what's pk of x is the set of k classes of k cycles, such that alpha can be written in this way. So it's a complete intersection of ample divisors plus beta, where beta is again the class of k cycles such that it is, I call it numerically semi-ample, which means that the numerical base locus is empty. Okay, so a divisor is semi-ample if and only if the base table base locus is empty. And this I call it numerically semi-ample, but just for convenience. So this is the cone of positive cycles. Of course, this cone for k equal n-1 coincides with the ample cone. Okay. But in general, we will see what it does for us. So I have two theorems. Okay, in fact, this theorem holds on any scheme, so let X be a projective scheme. Dimension n. And let k between 1 and n minus 1. Okay. So let alpha be a class. Then we have the following result. So alpha is self-effective. Sorry, big. Alpha is big.
How do you define intersection? How do you define intersection?
Oh, no. In this case, I'm not using intersection. In fact, I will not talk about net in this case. Okay. The introduction I was in a smooth variety, but here for this result, I don't need intersection. Ah, you mean how to define numerical equivalence? Numerical equivalence is two classes are numerical equivalence if they coincide against chain classes of vector bundles. Okay, this is Fulton's standard definition. Yeah. Yeah. And it's, as far as, for me, it's rather mysterious, actually. I don't understand it very well, but in any case. If you want, you can continue thinking that is smooth. because I will not use subtleties about numerical equivalent for singular varieties. I mean, they are important, but I will not use them now. So, alpha is big if and only if p plus of x is properly contained in x, okay, alpha is properly contained in x, and 2, alpha is in pk of x if and only if p plus of alpha is 0. Okay, so if you remember before, this is the same for divisors. For now, here we are in cycles, and to say that the augmented base locus is empty means that alpha lives in this column. Okay, and then I have theorem 2, which is similar for B minus.
Sorry, can I just ask before you go?
Yes?
Take P3 and blow up a point, and take a line inside the exception divisor. This would be, and if you maybe add some ample to it.
Yes.
This is in your positive form?
A line inside the exceptional divisor? I don't think so.
Because it moves.
In the exceptional divisor.
It doesn't have a base locus because it moves in the P2.
Oh yeah, right, yeah, I think so, yeah.
Okay, so but it's not net.
Yes, okay. Good, yeah. It's not that in the sense of, yeah.
Because it
Yeah, I understand, yeah. Okay, so theorem 2. This is a little bit quicker, but maybe not so different from the other one. I will say why in a moment. So x and k and alpha is above, as in theorem 1. And now we have 1. Alpha is self-effective if and only if p minus of alpha is properly contained in x, and this is again the same as divisors. And 2. So here I can prove this. I can prove that if p minus of alpha is empty, then alpha lies in the closure of P2. Okay? And by the way, the implication from here to here, I need k uncountable. K is the base field, okay, uncountable. And this implication from here to here, I just need that the variety over k is not a union of countably many proper subvarieties. So I need k uncountable. Okay. And in fact, I think the opposite of this is also true, but I will comment on this a little bit later. Let me see what time is it. Okay, so I have 15 minutes. So,
25 minutes.
25?
Yes.
Oh,
No, 15.
15?
Yeah,
Yeah.
what? 15 minutes.
Because I started at 5. So
Yeah.
I have 15 minutes, that's fine. So, in fact, I'm going to sketch a proof of theorem 1 now. So, 4. And if I have time, I will do also theorem 2. Okay, so this is based on 2 lemmas. They are actually very simple. In fact, everything is very simple. Huh? Nothing really. I will not prove these 2 lemmas, but they are very simple. So, if you have alpha and beta, any 2 classes, then the numerical base locus of alpha plus beta is contained in the union. lemma 2. This is a little bit trickier, but again, it's not very difficult. Okay, so now let A1, AN minus K ample divisors. Then, for epsilon very small, positive but very small, we have that the numerical base locus of A1 times AN minus K minus epsilon A to the n minus K is empty. So if I remove a very small ample, then I get empty numerical base locus. Okay, so given these two lemmas, how I will prove theorem 1. Okay, so let's see. Maybe I can do it here. No, this is not okay. So maybe I'll do it here. Not so here.
So in that right formula, I suppose the numerical basis of A1 to A minus K would be empty, right?
Oh yeah, of course. Yeah, because they're ample, so you can move them everywhere. Right.
So
But the point is that if you subtract something, you can do this. But again, I mean, the proof is more or less what you said. I mean, just adjusting this. Okay, so let's see. So proof. So I want to prove theorem 1. So I want to prove 1 first. So if alpha is big, then, as I said in the remark before, you can write there exists A1 AN minus K. So this is by the remark which I raised. AN minus K ample, and there is this E effective, such that alpha is A1 times AN minus K plus E. So of course, B plus of alpha is contained in V num of E. Right, because it's intersection of all these. One of these is E, so it's contained in the binum of V. But binum of V obviously is contained in the support of V, which is obviously properly contained in X. Okay, vice versa. If B plus of alpha is properly contained in X, then what happens? Then happens that one of these, at least one of these, is not X, right? So again, there exists A1 n minus K ample, such that the numerical base locus of alpha minus A1 times AN minus K is properly contained in X. Okay, and then what does it mean? This means that there has to be some effective cycle linear equivalence to this, numerical equivalence to this. Otherwise, this numerical base locus will be all X. Huh? So there exists just by this definition, such that the class of E is alpha minus A1 times AN minus K. And so this means that alpha is like this. C, and since E is effective, this means that alpha is big, again by the remark. So I said alpha is big if and only if you can write it in this way. It's like for divisors. Okay, so this proves 1. And now we prove 2. So maybe I'll rewrite it here. Did I erase pk? Oh, I erased pk, so I better rewrite it. So pk of x is a set of alpha that can be written in this way, right? So the intersection of ample divisor plus beta, and beta is numerically semi-ample. Okay, and then now we want to prove 2, which says that alpha is in pk if and only if p plus of alpha is empty. Okay, so one of 2 directions is obvious, which is this, because of course if alpha is in pk of x, then you write it as above. And so, but by the very definition, b plus of alpha is contained in num of beta, which is empty. Which is empty, and so also b plus of alpha is empty. And vice versa. Okay, so vice versa we use this. Okay, so now we have that this guy is empty. So maybe I can continue here. Okay. So now we have b plus of alpha empty. Okay. So never b plus of alpha, even though it's intersection of any ample divisor, this is set theoretical. So I can choose finitely many of them and set theoretically get intersection. Okay. So I mean, not because it's empty, this is in general, okay, but now I will use it in the empty case. B plus of alpha is empty, so let AI1, AI n minus k ample from 1 less than or equal I less than or equal S, such that B plus of alpha is the intersection I from 1 to S of this class. AI1 times AI n minus k. Okay? And now, okay, but in our case this is empty. This is true in general, of course, but in our case this is empty. And so now what do I want to do? Well, so I want to use this lemma here. So I want to pick an epsilon that is good for all AIs. Okay, so by lemma 2, there exists an epsilon such that the numerical base locus of AI1 times AI n minus k. I pick an ample divisor A, any ample divisor A. Minus epsilon a to the n minus k is empty for every I. This is finitely many, so we can do it. Okay, and now okay, so now what do I do? Now I study. So I guess I can erase here. And we are trying to prove this. Okay, so now I can consider this guy, the numerical base locus of alpha minus epsilon a to the n minus k. Okay. So what's this? Well, I can write it like this. It's very, you see, this is very simple. I add and subtract this guy. So alpha minus AI1 times AI n minus k plus AI1 times n minus k minus epsilon k to the n minus k. Okay, now I use lemma 1, which is going to be contained by lemma 1 in the union. Minus epsilon k to the n minus k. On the other hand, I just said that this is empty, right? This guy here is empty. So what do I get? I get that this guy is containing this guy for every I. Okay? Now I can erase these two lemmas. So I get that binom of alpha minus epsilon k to the n minus k, this is contained in the intersection I from 1 to s of these guys. A1 times AI n minus k, but this is just B plus. Okay? And B plus of alpha by hypothesis is empty. So this guy is also empty. So if I let beta equal alpha minus epsilon k to the n minus k, then the numerical base locus of beta is empty. And of course I can write alpha, I can write it 1 over epsilon to the 1, then minus k root of epsilon a n minus k. Well, I mean, this is not needed, but in any case. So it's intersection of bumble divisors plus beta. So I wrote alpha in this form, and therefore alpha is in pk. Okay, this concludes the proof of 2. Thanks. Perfect. Okay, so I will finish with some open questions and some remarks. So, questions. So 1 is pk of x an open cone? If the answer is yes, then I can prove all the results of Ein-Lazarus and Satz and Eigenpop. They are done for divisors. I can generalize it to any k-cycle. So, and by the way, I've been discussing with John Christian Otten, and it seems to be that this is the case. Okay, so maybe later on, if everything works well, this should be true, and then everything will work out. And second, what is the relation of pk of x, the cone of which I call the positive cycles, with other cones? Positives of positive cycles. Maybe I should have said it before, but I didn't because of lack of time. There's been several other possibilities for positivity of cycles. Some were introduced by Otten to define what is an ample subvariety, and therefore also an ample cycle. There is some definitions by Fulger and Lehmann that define several cones with several different positivity properties. I can prove that some of these are this is contained, or some are containing some of this, but I don't have a clear picture. And also the other thing that's very important is that now there is a Zariski decomposition of cycles. So how this positivity notion relates with Zariski decomposition? So with this, with other concept positive cycle or with Zariski decomposition? Well, since time is up, I will leave with these questions. Thank you.
Thank you very much. Question?
I have a couple of questions. Supposing you fix one ample divisor,
Yes.
I call it H, and instead of using A1 to K, you just use powers of H. How would the story change?
If you use powers of H, you get the same thing.
Same thing.
Yeah.
Okay. So second question is.
Yeah, I could simplify it.
Second question is, if pick equals Z, and if I get a projective space or hypersurface, for example, then I can define the degree of any subvariety.
Yes.
Of any cycle. Is your positivity the same as positive degree?
How do you define the degree?
Using the unique ample divisor.
Intersecting with the cycle. Yeah. If ample is the same as positive, if positive is the same as positive degree.
Yeah.
Can you have like an exceptional divisor?
I'm not sure because yeah. Because it's clear that it's positive degree by this definition, but the opposite I'm not sure if it would be true. Probably not actually. Yeah,
So,
like exceptional divisors of this type.
Okay, so in a specific case, projective n space itself, under what conditions is a subvariety positive?
This I don't know. I have to think about it.
No.
I haven't thought about it.
Projective space. I mean, they're all numerically close.
Only one numerical equivalence class of
Right. There's only power of a line. Yeah. Or a projective space of the correct dimension. Yeah. Right.
So there, I guess if the degree is positive, that would be positive.
And that moves. I see.
Yeah.
So I will say that in that case they can try.
Yeah.
But in general, I don't think so.
Maybe.
I have to think about it, but I don't think so.
Yeah. Is it possible to try to define it without projective? I mean, you could think about maybe a positive curve or something like that without needing complete intersection. You could define it for, I don't know, scalar.
Well, yeah, you need to replace in the definition. You need to replace this with some other positivity notion. Like, for example, one could use ample subvarieties in your definition, but I don't know if they coincide or not. So this is part of question 2, as a matter of fact, because you can define other positive concepts and then they need to be compared. But I haven't worked on it yet.
Maybe it would be some kind of measure on.
Of course, on a compact complex variety, yeah. That also can be done, yeah. But I don't know the answer. Sorry, you were asking something else?
No, you answered it.
Okay, no more questions. This is again.
Okay, thank you for Thank you to everyone for coming, for contributing, and congratulations once again. Good luck. I know the content has a birthday tomorrow. So
Siamo in codimensione.